对吧？我们韩国人没有的日子。Okay, so we don't have the Korean originated the word for 불그스름한 거, 크로스름한 거, 누르스름한 거 있는데 우리말에 녹색이란 말은 없어. 녹색은 중국말이지. Okay. Okay, we have three colors. Wow. You have a four color. Who are you? Okay, maybe this is not a fair question. In the video, I said Rothschild developed a calcium signaling probe, but he did not get the Nobel Prize by this. I will teach you what it is later, but I didn't teach you. So that was a little unfair, but you could find. Okay, so this one I didn't have a chance to teach you critical relation protein. So this is expressed the colorful protein in the cell. That's very powerful technique too. So I believe this original work, this one single paper got more than 20,000 times citation. That's amazing. I published about 100 papers so far, but all together, those cited on all together, that's still about 20,000. Only one paper, okay? Value is 400 papers. So that's a really high impact one. You have seen those blinking images in the video. So I just wanted to let you know. But later, this jet technique is a really powerful technique. You may encounter if you study biology or cell imaging. 오, 최근 맞췄네. 이거는 안 가르쳐준 거 아니야? 그래서 얘기했나? 안 했지? 안 했지만 이만큼은 맞췄어. 그랬는데. Yeah, the outer color is a red color. We may think we know enough about the rainbow. Really? Do we really know that much? We'll check. Light is electromagnetic wave, not electron beam. Electron beam is electrons flow. There's a beta ray or cathodic ray. 약간 different name it has. This electromagnetic wave is electric changes induce magnetic change, and it's coming together in magnetic field. This kind of a changing the property of the movement. That's the electromagnetic wave. Visual light is from 400 nanometer of violet color to 650 range of the red color. You may see maybe 700. I cannot see that anymore. So the vision is getting narrower and narrower. Same thing for the hearing. Make it a little better. Okay, great. At least you are listening to me. Diffraction limit. 회전 단계. Okay, this is the physical limit of the how small we can see. Light goes, and then it's about the half of the wavelength. If light hit that object, it changes the path. That's what we call diffraction. If it changes the path, then we cannot see that very clear. It looks blurry. Because of that, the physical the limit, optical microscope, the best thing we can see is a little bigger than this. Smaller than that, we cannot see clearly. So to overcome that, there is some technique so-called super resolution technique or near field. That's advanced technique you may learn in different classes. Okay, human cell is about the 10 micrometer, so we can see human cell. Accuracy is about 1 micrometer. That's not much bigger than, too much bigger than the diffraction limit. That's why if you have a not very well focused, even though very well focused one, actually a maybe small circle was just a dot, just a blurry dot. Virus is much smaller. That means the virus size is even below the diffraction limit. That means the virus, we cannot see the shape. It just looks like just a one dot. The image you have this kind of the head and then the leg, that's not optical microscope, that's electron microscope. That's a totally different technique. Optically, the vision wise, that's related to the wavelengths of light. So that has the kind of limit. Okay, based on this, so today we are going to talk about light and imaging. Right? 이상하겠어? 수현이 누웠어? 어? 왜, 뭐 이상한 거 보여줬나? 뭐야, 누웠었어? 비웃은 거야? Okay, so today we are going to look at the light. So let's think. If you want to study material, okay, all of us so-called natural science people or engineering, if you want to study chemical material, what's inside here? We cannot break it. How can you study this? Usually we use our five senses, and this is for feeling, or maybe this feeling is a contact feeling, or all senses we have, but you know, the vision is most information dense, the sensing. So people say we have about 90% of the information we get from the vision. Vision, in a sense, we can say this is an optical sensing, and that means we use an optical receptor or photoreceptor, and we change that or process that information here, and then we get different information. And this is 90%. And there is some terms related to this, which was some of these, let's say chromosome. Chromo, that means the color. So color means it's a different wavelengths of light, the visible light. Some wavelengths selectively in sense, that's color sensing. Chromo, and chromosome is 염색체 that is condensed DNA form. And condensed DNA form, why it is a colorful body? DNA has more trend to observe different materials, and then it can be stained easily. So chromosome, if there are any dyes, they are observe them and then make those chromosomes better stained. That's why the cell, those chromosomes is better visible. That's why this name was given, chromosome. That chrome is not DNA itself color. That's observed with different eyes color. That's chromosome. Chromatography. So usually we think this chromatography is a separation technique. Put those material in and it's separating. Long time ago, these days we use UV lamp or different colors making technique later, or maybe UV detector we can use. But long time ago, if you think about it, you don't have enough analytical technique. If it is not colorful material, we cannot use the chromatography. So in the beginning, this technique has been used to mixture of colorful material. That's why colorful material graphene means is writing. So that is writing this band. So there also the terms of the color is included. And scope. Scope means scopic, that means it's a seeing. And telescope is seeing the far away stars. Microscope, small things we can see. In a sense, this technique is very similar. Anyway, it's a small thing, we want to make it big, and then we can detect it. Bigger than diffraction limit. Then, can we use a telescope for microscope? If not, what's the difference? It's too far away, that's why it's small. We enlarge it and we see it as a telescope. It's too small here, and we enlarge that and we see that. Basically, this is enlargement of the object. Then why we cannot use telescope for microscope or vice versa? What's the difference? Real size is important. Only important thing is whether we can see it. The size of the image which is to our eyes. Real size, it doesn't matter. Star is very big, but if you draw the star very small, okay? How far is the problem? Why? It's focus. Okay? Focus is different. The far away material, it should have the focus should be far away. Because our eyes can sense only passes through a small hole, and then that focus should be there on that object. If not, everything looks very blurry. That's why enlargement of is the same, but focus is different. Okay, utilizing this, now we use to analyze the materials, we use the light a lot. Okay, that's the thing. If light emits matter, what kind of interaction is possible? Light and material or matter molecule, if they interact together, what kind of interaction is possible? What happens? Exciting. Exciting means which excite which? Light excites material, then what happens to the light? Just like the pharmacokinetic or the pharmacodynamic issues. Light excites material, but what happens to the light? Observed by the material. Light is observed by the material, right? So that means obstruction. So, first, if light meets other material, material can observe sometimes. Or, what do you say in English? Reflection. Anything else?
Diffraction. Diffraction.
Say again?
Diffraction.
Diffraction. And diffraction to catch. That's it? Transmission is a possible. Transmission is a no interaction. No interaction is just a passes through. No interaction. It's also possible. radiation. Radiation means it's generating light. It's an interaction material with the light. I'm asking about the interaction between light, already generated light, and material. Diffraction. And why the sky is blue color? Scattering. One of the topic of today is the fluorescence. So maybe the one meant the radiation as emission. Okay. Observed energy can be stored and then it can be re-emitted. Then emission is another thing. So big class wise, let's think about the reflection and scattering. How they are different. Reflection and scattering. Daniel, how is it different? Why is that same?
Reflection, the angle doesn't change.
Angle doesn't change. Scattering?
It's like random.
Random. And is that the same phenomenon or different phenomenon? Is it different? There is some difference. But if you think about molecule has electron, and all the interaction here is light and electron is interacting. Okay? Electron observed the light. Observed the light was kept on electron as re-emitted. Electron interacted with the light, and electron was irregular structure, interact and then it's kind of randomly redirected. That's the scattering. If that electron is evenly distributed on metal surface, then this direction is the same direction it is reflected. This is a ordered scattering. In that sense, these two are physically same. Also, diffraction or this is a deflection. Sorry. Refraction. Refraction, culture, all of these are kind of ordered scattering. So then, if you just classify those interactions between light and matters, basically either scattering, that means almost happening at the same time. Light comes in and interacts with the electron, somehow same direction or different direction, it moves out almost right away, almost without a delay. That's scattering. The other way is the material can observe. Which part of the material? Electrons. Electrons observe the light, then that energy is stored in the molecule for some time. After nanosecond range, it regenerates the light, then that's a fluorescence. If they hold the milliseconds or longer, phosphorescence. So if you classify those interactions in big way, 1, 2, 3 possible ways. They have a different technical name: X-ray diffraction and fluorescence emission, or refraction, scattering, Raman scattering, or different names that are given. But basically, it's a 3 class of the interaction you can think of. Now, based on this, let's just say any study to analyze or to study the material's property, we use light. That kind of a study field, what we call. Optics is that's one of them. Optics, you don't consider the wavelengths. All the light comes in and then it's a passage change. That's optics. If you count or if you utilize specific wavelengths, that's not whole light. It's part of the light, not 광학. It's a 분광학. It's a spectroscopy. Okay. Spectroscopy means we use a spectrum and then we see. That's a spectroscopy. So if you don't use the light, any wavelength of the light, If you don't use electromagnetic wave, you don't call it spectroscopy. Spectroscopy, we can see only very small range of visible light. Spectroscopy, you can use all the wavelengths of the light. So, spectroscopy utilizes spectrum. This is the spectrum. From 400 nanometer to 650 nanometer range of all the wavelengths, the full bundle of this color is called as a spectrum. And utilizing spectrum, we see that's a spectroscopy. So we have some technique utilizing mass. Mass spectral. You cannot call this a spectroscopy because in the mass there is no light involved. There is magnetic fields, but there is no light. That's why this technique is called as a spectrometry. Very rarely you hear somebody say mass spectroscopy. They don't know the definition of spectroscopy. Very rarely, if you go to Google and mass spectroscopy, there is one or two couple of the articles you can find. That's zero. Okay. So then, color is generated from white light. So everything is combined, already I explained in the video today. How can you generate all the colors? In the lab? How can you generate the spectrum? Using prism. And then you can separate them. Okay. Definition of color is not easy thing. So if you define the color, how do you define? This color may have red component and mixed together with maybe a white background maybe. That's more naturally coming to our minds. And how could you think that if you combine all the colors and it becomes a white color? That's actually a little contrary to our perception. We feel white light as a background. And there's something is added we feel. But reality is actually it's removing some part of that, and we see leftovers as a color. So that's why the color light was very difficult for the object, for the scientists, for hundreds of years. Today, we perceive that we know that, but we should really think whether we know how much, and we really know about that. Always we need to think. So this white light has been used as our background. I try to explain in the video clip. That's because this is the strongest light in our environment. If you sense that as a signal, then it's very difficult to distinguish different colors. That's why any strong light in our environment, we just everything out and then turn it down and turn off our signals, turn off our sensing signals, and make those sensory systems higher. And then we don't sense it anymore as a signal. That's becoming background. That's what color. In nature, what is the source of the spectrum? Spectrum. Right, rainbow. So then you also say that outside of the ring is the red color. Okay, that's good. How can you say this the outside? Because that rainbow could be eventually goes a circle. Then you can say which is the one with the out and in. So let me give you a question again. Now we can define the inside and outside of the rainbow. Which side was the brighter? I'll show you. Outside was the brighter. Middle? Because we don't count the middle. So this is the color of the band, and outside of red, inside of violet, inside the space, outside the space. Which side is the brighter? Outer side? So outer side brighter. Inside the brighter. Gave up? Come on. Outside. At least half and half the chance. Inside. What did I say? Huh? Get out. Very interesting. Always inside is brighter. Really? Not clear? always inside is brighter than outside. Can you explain? Why the blue sky is a blue? Nitrogen is a blue color? No. And what does that mean? That sounds like our 선생님이. What did you say? You didn't say the sentence.
컬러 뭐잘 키워줬어.
Choose one.
세 번째 거.
No.
아 스케치. 해주셨다. 설라.
Shorter wavelength is a better scattered. Shorter wavelength is a better scattered. It looks like it's a scattered but color. There, shorter wavelength and also even the ultraviolet range of the light is a better scattered. And then change its color a little, and then make it more light, make it visible to our eyes. Even though rainbow, we think we know, but there is something we don't know there too. Now rainbow, well, how is this made? It's like go in and reflection first, and then reflection, and then reflection again. When they reflect, this is similar to prism mechanism. One time and two times. Shorter wavelengths is reflect further, and you make this kind of color. Sometimes, if there's one angle, we can see the rainbow, a little higher degree, it can be reflected twice. So this is a one-time reflect, and one-time reflect, and two times reflect, and it can generate like this. And sometimes we can see twin rainbow. Now we have three layers, right? So by looking at this, first rainbow, second rainbow, we have an A, B, C range. Okay, we just talked about A. A's outside was red color. By looking at this, how about the B rainbow? This B rainbow's outside is that's a violet because it is reflected one more time. It's reversed. Okay, that's good. And second question, 하나 줬나? 오늘 안 받았어? Now second question, A, B, C area. Which area is the brightest? And which one is the second? A, B, C. Now we saw those color order. A, B comparison. Which is brighter? We already said. A. B, C. Should be C, right? That's part of the range. Then A, C, D. Is it? A, C, okay. Again, this scattering may be the largest, but that's why I said most bright. And outside here, this is a little more bright, and then this is the darkest. Okay, this is a rainbow story. And all of those, among those electromagnetic waves, we utilize a very, very small range here. Why do we see only so small range? Our vision occupies over 90% of our sensory information. It's a lot of information. But still, that's a very, very small range. What if we sense here or here? What could be the problem? If it is getting shorter, if we can sense it as a sensor, our sensor may not survive. That's too high energy. UV heat, then it can easily break most of those organic molecules. If it is longer, what's the problem? Too much noise. So that's why this is kind of a selected range, but depending on the environment, some microphones they can sense a little further this side, while some they can sense a little further to this side. So anyway, this is what we chose. And then among them, we chose three color range, so-called RGB range you see. And I said for the white color generation, we make our sensor higher, if it is exposed to too long. This is the example. So look at this spot. I think that you have seen this kind of tricks, but I'm not sure whether you ever thought that what that means. Okay? We have 3 color sensors, RGB. If you look at that spot over, let's say, 1 minute of time, and then those sensor systems, if you see more, then they get tired. And then after just 1 minute, and you see temporary sensors, the images showed up on this white background. That means the sensor is not used. They get more fresh, more signal. That's why I found the white background. You see those temporary colors. That means those are dynamic, the speed of our eyes are very, very quick. Within 1 minute, we can reorient our sensor system and then we change the definition of the white color. And we change those color sensitivity. Okay. So that much of the sensory, and here as you can see we have RGB 3 colors. But if you are designer of computer screen, okay, to make full color range coverage, this is B. RGB, this is just a general sensor, and looks very strange. R and G are too close. If you have a very close sensor, two of them, then maybe differentiating different color is not good. To make better, you may want to have the B, G, R like that. Then you can get further different definition and you can express much better color expression. Actually, QDOT or any kind of a Samsung, LG screen, they utilize not our system. They utilize much bigger system. That's why they can make much more brighter and also the more distinguishable different colors. Then why we have this kind of shape? I explained that those ox or the dogs, they cannot see more than 2 colors. And even chimpanzee, gorilla, they can see 3 colors like us. But a little far, the monkeys, they cannot see the 3 colors. That means originally they had only 1 receptor here. And that was on the evolution, that was divided into 2. But they are not too far away yet. So that's why you can see. Then seeing 2 color and 3 color, is that really big difference? Maybe I have shown you this picture, 3 color images. And if we have only RG, the RG combined together, then usually G and R cannot be distinguishable. Then it may be difficult for them to see green light and red light discrimination. That's why if you look at those the signal of the lamp, there is some extra band there too to show that this is red color or this is green color or this color red. So it looks like nothing, but if you look at the natures, this is a 3 color vision. If you look at this in 2 color vision, it looks like this. Now it's almost impossible to discriminate the green and red. Well, it's just a small echo issue that we can give up. But in this case, all the time I was curious from when I was young. They say this tiger's color is kind of the coverage color for open. But they look too obvious to us. This color and this color is very different. How come it can be, camouflage the colors? It's a wrong strategy, I thought. But as we just said, most of those animals, they cannot distinguish red and green. That means the tiger is like this. Now that's much different, isn't it? Then why didn't they choose like green rather than reddish color? They have too much green in the field, and then making green color is more difficult than making red color. We learned about those particle box size lengthening. Making it longer is more difficult than making shorter. That's why maybe tiger chose maybe reddish color, then they can just observe green color. To make a green color, you need to observe red color, and you need to make the box much bigger. That's more expensive. So because of this, let's just say this is sunset or sunrise, and if you cannot see the three colors, they look quite boring, the sunset, like this. So two-dimensional information versus three-dimensional information, they're hugely different. Now, if this is applied to the science, so maybe I should review. Bacteria, this is quite good, except the microscope. And bacteria, it look like just like this, but we cannot distinguish them. If you add staining material, then positively stained and negatively stained, and this is example of bacteria segregation, and we learn that for this gram-positive, gram-negative, different cell wall structure. This picture is observing image. In contrast, this image is a fluorescence image. How can you say background color? Background color, this one was white color. To see this kind of a clear color, you need to remove the other color almost at least more than 50% or 90%. Then you can see very vivid color. To do that, it implies that you need to have a lot of materials, time materials. It's very difficult to do that for live species. Most likely those are the dead images. In contrast, in the fluorescence images, background is very dark. Even though your additional dye is a very small amount, if it emits the light, then there will be very small amount will be not. Because there is no comparison with the different reference. So when we look at this question, fluorescence suppression indicator, how does it indicate what's penetrating inside the cell, not killing the target cell? Okay, good question, so let's think about it. So here is a T cell and B cell. Can you distinguish what's the difference between these two cells? If you can pick it up, and I will give you 2 points. If you can find those differences in that picture, your eyes are really, really strange because there is a cut. So that means the T cell, B cell, they are very similar to each other in terms of size and shape. It's almost impossible to discriminate in real the microscope. Then how do you discriminate them? Usually we utilize those different protein expressed on the cell surface, so-called biomarker. If it's only expressed on here, this is a B cell biomarker, then we may generate at least thousands of different proteins. And these are one cells of the protein, two different, the two-dimensional, the chromatography, and then we needed to take out only one cell selected one. Is it easy? Well, this is B cell, this is B cell. Selected. This is not cheap. This is real data. Can you find which one is more expressed here, not here, or vice versa? This is chromatography. If you have done TLC, if you spot and then run it on the solvent, if it goes up, and you can calculate those distance alpha value. Those alpha value is always give you the absolute number. Day to day, it's a change. This is 2D. If you run it this way and then run again this way, even though same sample, you may get slightly shifted the images all the time. Right? Then how can those come? What kind of problem? Here's one trick. You collect all the proteins and you label them with green dye. And you collect all the cells, all the protein, and you label them with red dye. Protein is much bigger and dye is relatively small, and that divergence of the effect is small, let's assume. And you mix the two samples together and run it together. Then, even though there is a slightly different, the variation happens, at least that happens together to both of the samples. Then, majority of the sample, they may look like yellow color because their colors are black. But some spots, they look red color. This is selectively expressed here. Do we find that? That's this spot. This is here, not here. If it's a green color, okay, this one, here but not here. So this is the one trick you can do. So by doing this kind of experiment, you can select those candidates of B cell biomarker or T cell biomarker. So if you found this biomarker, then one thing you can do is you add the probe from outside. So this probe is binding to this biomarker. Biomarker is the material inside the cell. Probe is we put it into the biologics. Some of those probes, they change its color, then we call them sensor. That means sensor is a special type of probe. So then, in many cases, the scientific approach is the hypothesis-driven approach, we say. So we need to have a hypothesis or concept. Then in this case, a hypothesis means most likely we know what's the biomarker. If you have the idea of the target biomarker, one way is we collect those biomarkers, let's say that's a human protein, and we inject that into the mouse or rat or rabbit. Then there is a foreign material, and the animal will generate antibody. Among those antibodies, then we select best binding antibody, monoclonal antibody, and label them with fluorescence motif. Then, in this case, this is a biomarker, and this is a probe. Biomarker, sometimes, usually we think this is a huge molecule, but epitope is can be very small. So it's not size the comparison, it's a functional comparison. Biomarker and this is a probe. If that biomarker is on the cell surface, then antibody, we can make it and then add, then we can bind. But if the biomarker is inside the cell, even though you make antibody, the problem is antibody cannot penetrate the cell membrane. In this case, you need to fix the cell using formaldehyde, and then still membrane is there. You add the detergent and dissolve some part of it. Then you can send the antibody inside the cell. Then maybe we can visualize this microtubule structure, healthy microtubule in muscles. Hexotrypsin one breaking up, I showed you this before maybe. And then actin, we can see multicolored together. And maybe if you dissolve those all the lipid molecules from brain, then by adding several antibodies, you can show those neurons structure. So it looks like a very dynamic structure, but actually the real situation is you kill the cells and then dehydrate. So kind of situations. So live cell versus the dead cells, the important part, maybe I showed you this before, the receptor. That's the big one. So usually we said outside is the positive charges, inside the negative charges, but most of those possibilities, they are negative charges. That's why in real situation, outside is less negative charges than inside. That's why negative charges molecule has a problem to have access, and positive charges molecule has a better to access. Neutral molecules is doesn't have that kind of problem. So that's why following the reference below, penetrating this membrane, you need to have a reasonable penetrance. So that's why if it has reasonably positive charges, then hydrophobic can bind to the mitochondria, and neutral and reasonable can go to the ER or go to the nucleus. If it has very strong partner, then it can go to nucleus. So I try to show you several examples in video clips, and this is a nucleotide, and then this kind of mitochondria, the dyes are mitotracker, lysotracker, or ER-Golgi tracker. Kind of thing has been developed in the different colors. So those has been used for live cell distinction so far. Calcium imaging. For those calcium imaging, the problem is like this. This compound, the pillar 2, this single paper that got 20,000 citation. And I showed you some images too, but I brought 대한민국 총력자 58만 명. So here, this is the blinking signal is those calcium dyes sense calcium which is turned on. And this is real-time images. This is a neuron image. And on those neuron images, and neuron has a firing effect. I showed you found is a white color. Even can say here. Calcium was stuck behind. Amazing. Enjoy all those. So here, this blinking light goes up, neuron fire, and then generate calcium wave, and those calcium sense the interact with those calcium dye, and shows this kind of signals in real time. So in this case, how this is possible? The small molecule could go into the cell. I showed you two examples of Thailand. So this sensor molecule could go into the cell and it can bind to the cell, to the calcium. And only when it is bound to the calcium, it turns on. It shows those fluorescent signals. Okay, then this was also I showed you a little bit how to make those the colorful molecule. One trick was to combine this conjugated system like this. And then this conjugate system getting longer and longer, then it can absorb the light. That's what we said. Now then, if you have two fragments, so one fragment and two systems you have. If they does not reach those 400 nanometer range, then they are not colorful. Only when if you make those molecules move together and make the conjugation in the middle, then those molecules, only conjugated molecules, they can become colorful. So then depending on the size of these boxes, maybe this is 200 nanometer, this is a 300 nanometer, if they meet together, they observe 500 nanometer light. And if you prepare different building blocks here, if you combine them, then you can generate different colors. So next week, we want to do this kind of experiment to generate the different colors. And now next week, we'll have two groups. One is Tuesday group and one is Thursday group. Check it out, where is your name. And you may need to bring your laptop and glasses and then note. If you have a problem for this, the assignment, then you can talk to the Navion, you can change. Or you find your partner to change, and then you can assign. So next week we will have this experiment sessions. That's why we had a pizza today. Next week we will be separate the two classes. One for Tuesday, one for Thursday. Okay. So your the TA, again we will send you more details what to do, what to prepare for. Okay. So the first time is the same as this class, starting from 2 p.m. We will finish maximum about 1 hour. Okay. Okay, before we like, not that can be fun. That can be really fun. One of the real reason is that I'm traveling to China from the Thursday for 3 weeks. So this is practically the last class with you guys. That's why I wanted to treat you with pizza today. And next week we will have to do this experiment with the Okay, before I close this class, I want to give you this question. 그렇든 어디서 가지고 가. 내가 벌써 올리겠구나. 항상 지금 남들이 받아다가 수업 직전에 올린다고 고생을 하다가 나는 내가 좀 조심한 것 같아. Okay, what do you think? We heard the photon is a particle by the experiment of Einstein. What's the size of a red light photon? We have a receptor, we have a molecule. So molecule we just talk about like this, these molecules, combine these together, so organic molecules. Maybe the size of organic molecule may be about 1 nanometer. About 1 nanometer size. Wavelength of a red light is at 600 nanometer. And and the material can observe the light, the photon. Okay. Then, what is the size of the photon, you think? 600 nanometer of red color light. Diffraction limit is of the half of that, 300 nanometer. The molecule which observes this is 1 nanometer. Then what can be the size of the photon? In many cases, when they say the dual character of the light, wave and particle, they use this metaphor of water wave. Water looks like a wave, but if you look at the water molecule, they are particle. Kind of a metaphor you may have heard. I think this is bad metaphor. When you think the diffraction are the limit, if the wavelength is, if this is light wave, maybe this should be reasonable size of the photon size. And when this meets the particle of a similar size, and they interact, their interaction becomes maximum, and then they can hit and then change its path. That is more reasonable. So that means if that light meets with particle, and this is material, and this is light, maybe even bigger than this. So this is material, this is molecule, and this is light. This would be maybe more realistic vision. Light is much bigger. It's hundreds nanometer. But the molecule which observe it is very small. So that means big light goes in and they hit the material, and then this observed. And then we hit. This would be more realistic picture. After the photon was defined as a particle, as a photon, and there's a material is also can be wave, right? Matter wave, which is in the sense they try to calculate the wavelengths. If that describes the size of electron's size, electron if it gets faster, it's becoming smaller and smaller. Right? Those wavelengths is wavelength is reciprocally proportional to momentum. Momentum is mv. Velocity is becoming faster and faster, then wavelength is becoming smaller and smaller. That means it's becoming more and more dense, hard needle. If it's slower, that is relaxed out, it's a bigger ball. Okay? More relaxed light with a bigger wavelength is a little more relaxed, soft on the ball. If it's becoming smaller and smaller, wavelength is getting smaller and smaller, like X-ray or UV, and then they becomes very hard ball. Okay. This one I wanted to give you my impression and my interpretation. I think this is a more realistic view rather than water wave. Photon is not small. Photon is light. Okay, so next week, as I said, 2 group experiment we will do. And then finally with them, now we need to change this. Originally I thought maybe that's a Tuesday, but somebody has the conflict of time. We change this into June 6th, Thursday. Tanya, is it okay? Okay, then everybody is fine. Then Thursday, 2 p.m. we have very similar format and also similar amount of the problem as we have seen in the exam. So it may not be more than an hour time. Okay, so this one next Tuesday, next Thursday we should change. Any question? Okay. you want. So for next week, I just want to give you a chance to see that the effect in reality. That's why no report is exam free. Okay, just enjoy. Already I made the problem, so don't give me extra work. In the final exam of the paper, you will see this date, but you don't know it. Okay. You can answer in Korean too. The problem will be given in English. We have two foreigners, but the answers you can give in Korean. You cannot use any electronic machines as before, but you can use any colorful pen, including fluorescence pen. Anything you can do, you can express your way. Next week is experiment. Final exam is the next week. Thursday. Yes, correct. You just need for next week. You just account only one place. There's a little too many people here, so that's why we divided into two. So this is the Tuesday group, and this is Thursday group. Okay.
시험을 당일하면 무슨
I'm not here. I'm in China. Hopefully, I can answer you by cut-off. I don't know. These days, if I go to China, then in several days, they will have the cut-off too. I'm trying to avoid that, but we'll see how it goes. But email will work. They cannot block the postal email, but they block the Google email. In China, no Google, no YouTube, no Kakao, no Naver. It will be tough time. But you have most of the problem, your TA will solve. Other question?
이번 시험에서도 예상 문제 제출하는 게 있나요?
이건 하지 말자. 그냥 relax. Last time you gave a little too many problems, I could not select. Just relax and just try to summarize what you have studied so far. Other question? 오케이, 이번 학기에 여러분들이 굉장히 열심히들 참여를 해줘서 굉장히 나도 즐겁게 수업을 했습니다. Many of you guys were very eager and then diligent and sincere for the class. So I enjoyed a lot to study with you guys. So this is the last day. Could you take one picture together before we